Hi everyone, so I am Sébastien Bardin, I am researcher at CEA in France. I will present our recent work on the deobfuscation of malwares, and this is joint work with Robin David and Jean-Yves Marion, who is working at L'Oréal, France. So in a nutshell, what is it about? We're interested in designing automatic methods for malware deobfuscation. We identify the problem of invisibility question as an important problem, which is mostly a blind spot to current automated techniques. And so we propose an efficient, robust, and precise method for solving this infeasibility question. And we will present some very promising case study. So first, why are we interested in malware deobfuscation? So typically in malware, you can either want to detect them, or in some kind of situation, you really want to understand them. So take the case of APT, Advanced Persistent Threat. So these are targeting malware written by experts and with lots of attack and defense abilities. At some point, once you understand you have been hacked by some APT, there is some guy somewhere which must try to find the malware, and until it is done, he must try to understand it in order to try to see what's going on and to try to mitigate the attack and to fix and clean what can be fixed and clean and to further improve the line of defense. But this is a highly difficult task because this kind of sophisticated malware are highly protected by obfuscation, which are meant to make reverse engineering very difficult. And so basically it is what we want to do to help this kind of malware comprehension activities by providing automated tools to allow to combat obfuscation, that is to identify them and simplify them. So reverse engineering is has a broad scope, but we're interested in the very basic first step here, which is just correct disassembly or CFG recovery for control flow graph recovery. So basically what we want to do is to find the set of instructions of the malware, and ideally it's control flow graph. Okay? It's very first step. But already on genuine code, it's not so easy because on binary code, you don't have a very clear separation on what is code and what is data. You have also this dynamic jump, like a jump AIX. In that case, statically, you cannot know where is the next instruction because it depends on the value, on the runtime value of AIX. So already it's not so easy. But in the case of malware, when you have obfuscation, it just becomes a nightmare. So obfuscation are meant to make a code hard to reverse. There are many, many different kinds of optimization, like you can think of self-modification, when you have a first layer, which write a second layer, which write a third layer, and so on. And at the end, you have a real payload. You have encryption, virtualization, code overlapping, opaque predicate, and so on. So many of these different techniques, and you can combine them to make the code really hard to understand. So as running example, we will use opaque predicate and code stack tampering, so just a quick definition. So in opaque predicate, you are using some branching condition, but which are ever always true or ever always false. And typically the trick is that the dead branch will point to some spurious code. And the goal is that the reverser of the analysis tool wastes its time in this spurious code rather than in the malicious code. You can also use stack tampering. So in that case, you will trick the reverser by modifying return instructions so that they don't go back to their callee, but somewhere else. So in that case, the return site will also be some spurious code, and it also hides the real target. So clearly, standard disassembly techniques are not enough. So on this small graph, suppose that you have one dynamic jump, and suppose that the red circle represents some spurious code. Then if you use some basic static analysis, disassembly, once you reach the dynamic jump, you cannot go further because you cannot find the dynamic targets if the dynamic jump is a little bit obfuscated. And you can also be lured into going into the spurious code. Basically, static analysis is way too much fragile versus obfuscation. especially once you have self-modification, encryption, and so on. It's just too hard. So there is another way, which is dynamic analysis. Basically, you run or emulate the program, and you see what happens. So by definition, you cannot go into spurious code. You can also find some dynamic jump. You can go through self-modification or encryption, but you can miss a large part of the program, which is a problem. A few years ago, some people like Christopher Kruegel or Soumya Dobre advocate to use dynamic symbolic execution in the context of reverse engineering. So quickly, what is dynamic symbolic execution? It comes from formal verification, and the key insight is that if you have a single path of a program, it's quite easy to build a formula which represents exactly the constraint that the input must obey to follow this path. Hence, you send the formula to a solver, and if you get some input, then you will cover that path. And if you iterate over that, then you will get a high coverage of the code. And naturally, it can be used in deobfuscation because with each new input, you will find new real execution path. So, and it's very robust because there is this dynamic part. So it's kind of dynamic analysis on steroids. So it's quite good to find new part and to complement dynamic, even if it's still incomplete. Okay, so is it the end? There have been very nice case study. So is it the end of the story? Not exactly, because basically dynamic symbolic execution can only prove that something is feasible. I can take this jump target, I can take this branch, and so on. But in reverse, in many situations, you want to answer more like some infeasibility question. Let us imagine that your dynamic analysis didn't manage to go to one particular branch. You would like to be able to prove that the branch is indeed infeasible, that it is some opaque predicate, or that some return instruction will always go back to its caller, to the good return site, even if on a strict way. Or if you have some dynamic jump, that you have found all the dynamic targets. And you can have more of this kind of question in every kind of obfuscation schemes. But dynamic symbolic execution and dynamic analysis, by definition, cannot answer to that kind of question because it would require to enumerate all paths, which is infeasible. Okay, so this is our challenge. We want to design tools to check the infeasibility question in obfuscated code, and we want to scale to realistic malware size, to be robust to obfuscation such as self-modification, to be precise and to be generic so that we can handle several kinds of infeasibility questions. So in the rest of the talk, I will focus on opaque predicate and stack tampering, but the technique can apply to many other obfuscation schemes. Okay, so our proposal in a few words, we call it backward-bounded symbolic execution. So the first key insight is that since we want to be very precise and to be able to reason about bit-level operation, modular arithmetic, memory, and so on, we need to have some symbolic reasoning, some logical reasoning. But in that case, in some way, we need to have some kind of finite path or finite constraints, finite something somewhere. So this is a problem. So actually, we can prove this infeasibility problem by reasoning backward in a bounded manner. So if we see infeasibility problem have some kind of reachability condition at some point in the program, by going backward, we are just gathering all the constraints, all the set of states of predecessors to this reachability constraint. And if at some step k, these sets become empty, then obviously our reachability constraint has no predecessor and it cannot be fulfilled, so it is infeasible. So this is an effective way to prove this infeasibility, and we have to rely only on a finite number of paths, actually a finite number of suffixes. So this is very good because we can use it with current solvers. And this is very efficient because it doesn't depend on some trace length or program size, but on the bound k, and we totally have control on this bound k. Okay, great. But still there is another problem. We need to do some backward reasoning on binary. But how do you do that? source code, C code, it's quite easy to do backward reasoning. But on binary code, you can have dynamic jump, you can have encryption, you can have self-modification. It seems to be very hard to go backward. What does it mean? So this is the third insight. We first start with some dynamic partial recovery of a control flow graph, like a dynamic analysis. It will solve partially some part of encryption, self-modification, dynamic jump, and so on. And then we do the backward bonding reasoning. And this brings robustness to the methods. So we get precision, we get efficiency, we get robustness, so everything is perfect. Obviously, things are not so simple because in formal verification, you cannot get everything for free. So our problem is that we got both false negative and false positive. So we typically have false negative because we have some backward bonded, we have a bound on the reasoning. So basically, we can miss some infeasibility proof because if the bound K is too small, we will not gather enough constraints to understand that the set of predecessor is empty. In some way, we miss some conjunctive constraints. Okay, this is the usual trade-off of this kind of reasoning. So the usual solution is to increase K. It is more expensive, but you prove more things. But here we can also have false positive. This is more original. So it means that we can wrongly assert infeasibility. Why is that? Because the control flow graph can be too partial. And in some way, we will miss some suffix. And it's kind of missing some disjunctive constraints. So we can prove that something is empty just because we don't have, we have missed some suffix. So here there is an interplay which is a bit problematic because if we increase K too much, in some way we risk to have some CFG which is far too partial, and then we will decrease false negative but increase false positive. Okay, but the technique looks so good, so we still want to have it and to make it practical. So we don't have beautiful theorem, that's it, but at least we do some control experiment with ground truth so that we can check that in practice we have very low rate of false positive and false negative. And actually we have also that if the CFG is complete and not partial, then we don't have any false positive. Okay, so we have done three kinds of experimental evaluation. So some controlled experiments with ground truth to assess the precision of the method. Some large-scale experiments on packers to assess the scalability and the robustness of the methods. And a case study on the external malware to assess the usefulness of the method. So briefly, for control experiments, we have taken some open source obfuscation tools so that we can clearly have control on the kind of obfuscation which are inserted, and we perfectly know where obfuscation are and where they are not. And we check for opaque predicate and stack tampering. So typically for opaque predicate, with a value of a bound of 16, we get some error ratio of 3.5% and no false negative. And this is quite robust to the bound K. Basically, with bound between 8 and 30, results are very good. Up to 15, it's still 50, it's still quite decent. And it's very efficient with 0.0 second per query. And we have also very good result on stack tampering. So in our view, this control experiment on ground truth value prove that the technique is very precise in practice. Concerning packers, why do we so packers are legitimate software protection tools. They are very representative of state-of-the-art protection. Basically, for basic malware, packers are the sole line of defense, and they combine many techniques. You can have self-modification, encryption, opaque predicate, and so on. So our experiments show that the technique scale on significant trace. It scales also on really realistic protection. So all the packers we are mentioning here are combining self-modification and other protection we are interested in. And we managed to find sometimes many opaque predicate or many interesting facts on co-stack tampering on this example, showing that the technique on realistic condition can find useful things. Finally, case study the external malware, which is part of the hacking tools that were used for the DNC hack on the last fall. We got 2 heavily obfuscated samples from this external malware. With a quick manual inspection, it turned out that there were many opaque predicates in them. So our goal was to detect and remove as much as this protection that we can. By using a technique, we were able to identify 50% of the code as spurious in a fully automatic manner and in less than 3 hours. When we say spurious, some of the code was dead because of opaque predicate, and some of the code was only used to compute the opaque predicate, so it was totally useless. So after that, we are able to pinpoint in the code where these spurious instructions are. And so, for example, for the first sample, from a code which has 500,000 instructions, we can see that only 280,000 instructions are indeed useful. So this was considered as a clear success of application of the methods. A quick discussion of potential countermeasure to our approach and potential mitigation too. So the first natural attack against our technique is to try to have long dependency chains to try to evade our bound. First, the thing is we do not always require to have a whole chain of dependency to be able to conclude to insatisfiability. For example, in the external malware, there is some dependency of length 230 something, and we can detect the infeasibility while our bound is only 16. So we don't always need to call all the dependency. Second, I think a really good mitigation against that is to use a more flexible notion of bound, not based on control flow, but for example, data dependency, formula size, complexity, or things like that. So together with simplification of the formula size, I think it's a very good mitigation. Then you can also insert many hard-to-solve predicates in your obfuscation scheme, because basically when we have some timeout, we don't know what to do with it. But the thing is, with our technique, we don't have normally timeout. So already triggering a timeout already gives us some insight. And then we can, for example, it can give us the opportunity, for example, to find infeasible patterns to then help the technique by pattern matching. And then you can add common anti-dynamic tricks, but we can also use the standard appropriate mitigation. So basically, this is the state of the art. We push the harm rate further so that we raise the bar for malware designers. So as a conclusion and takeaway, what has been done, we identify this infeasibility question as a blind spot of current automatic obfuscation techniques. We propose an efficient, robust, and precise method for solving them. And we propose control experiments and large-scale studies. We think that semantic analysis can change the game in the obfuscation as it complements existing approach, and it opens the way to fruitful combination between static, dynamic, and symbolic. It turns out that formal method can be useful for malware, which might be strange considering how complex it is, but they must be strongly adapted. You need robustness and scalability. In our case, we achieve this by accepting to lose both correctness and completeness, but in a very controlled way. And these results have been implemented into the BINSEC platform, and we are looking for collaboration and user. Thank you.
Many questions here?
Dongpeng Xu from Penn State. Very good job. I see you mentioned opaque predicate. So I see you handle all those opaque predicates that are always evaluated to true or false, right? Yeah. So as far as I know, there are also other kinds of opaque predicates. In different execution, the predicate itself can be evaluated to different values. So can you handle those cases, or can you provide some clues to detect them?
I am sorry, I don't understand well your question. Could you speak a bit louder, please?
What?
Could you speak a bit louder, please?
Oh, okay. So I mean, those are other kind of dynamic opaque predicates which the value itself can be different in different executions. So can your tool handle those kind of predicates?
Yeah, basically there are other ways to make opaque predicates. Like, for example, here we consider mostly arithmetic predicates, which are the easiest one for techniques. But you can also have, for example, opaque predicates which are built on, which take advantage of some multi-thread or things like that. In that case, it's more difficult without technique because the symbolic reasoning doesn't port on that. Does it answer to your question?
Yeah, kind of. Thank you.
Hello, good talk. I'm Ben Yu from Microsoft. One question. So if you are a malware writer, how are you going to defeat your own deobfuscation tool?
You have some, here you have some.
Follow-up work, right?
Okay, so there are more details in the paper. So yeah, I think these are quite interesting ways of seeing how to defeat our techniques. There is also some quite recent paper by Banescu and by Sebastian, Banescu and Debray at ACSAC last year, where they have some, the study of how defeating symbolic execution for reverse. So they consider the standard forward symbolic execution, but I think most of the technique may be useful in the context of this work, but clearly we still need to think. We don't always agree with Sebastian on what can be done or not. So clearly the cat and mouse game is still going on and we need to push it further.
So have you seen any like malware samples the tool cannot deobfuscate?
The problem with deobfuscation is always you never really know if you already deobfuscate the malware or not. What we can do is that when the tool pinpoints an opaque predicate, then we can go and see and, yeah, okay, this is really an opaque predicate or not. But you can have also many other kind of protection. And if we are totally not aware of the kind of protection, maybe the tool just miss it and something.
Okay, I'd like to talk with you offline. Thanks.
Right, let's thank the speaker again.